All right, welcome to section 4.1.1. We'll be defining inner products. Let's go right ahead and do it. Definition 4.1.1, let V be any vector space and inner product on a real vector space. V is a map that takes two elements of V and returns the real number. So just like the dot product. The dot product took two vectors and return a real numbers, that we're going to have the same thing here. And then we're going to ask that this inner product has some nice properties that are really the same ones we had for dot product. So if I take, this is axiom 1, if I take u dot v, it's going to give me the same thing as v dot u. So it's commutative. That's true for any u and v and v. Now, if I have u plus v times w, that's going to be u w plus v w. All right, so that's distributive. And then if I have a constant here, I'm going to be able to pull it out. All right, and axiom 4, that one is a bit different from what we've seen in this class. So if I take v dot v, that needs to be a positive number. Remember, for the dot product, that was the length squared, so it was positive. And if v dot v is 0, that means v was the 0 element, and vice versa. So this is the only element that dots with itself to 0. All right, so if I have a vector space and I create an inner product on it, if I take them together, I'm going to call this an inner product space. All right, so first thing we want to do now is look at an example. Consider the vector space V equals R2. R2 already has a nice dot product, but I'm going to define a different one. I'm going to define a new inner product. I'm going to take the inner product of V and W to be 1/9 V1W1 and 1/4 V2W2. All right, check that R squared is an inner product space with this inner product. So I need to check the 4 axioms. So let's do that right away. I'm going to take U and V in R2, then UV, that's going to be 1/9 U1 V1 plus 1/4 U2 V2. No arrows. I've removed the ones in your notes, hopefully. All right. Now, if I take V dot U, the only thing that's going to change is the order of the and components in the real multiplication. But of course, that's commutative. Multiplication over the real numbers is commutative, and so I can switch them. And I get that these are equal. All right, so axiom 1 holds. Let's try axiom 2. I need to take u, v, w in R vector space, so in R2. I want to look at u plus v w. That's going to be 1/9 the first component of u plus v, so u1 plus v1, w1, plus 1/4 the second component, w2. All right, I'm going to expand this. I'm going to get 1/9 u1 w1 plus 1/9 v1 w1 plus 1/4 u2 w2 plus 1/4 v2 w2. All right, so now you can switch and figure out what the other side is equal to, or you can just see from this how to put it together. So let me do it that way. I'm going to put all the u's together. And I'm going to put all the v's together. Sorry, that should be a v. And so I'm getting u and w with the inner product, and then v and w with the inner product. And so I got to the second side that I wanted. All right, we have 2 more axioms. So here for axiom 3, that's the one with the k, so I need 2 things in R, and I need an r squared and one real number. If I take k u v, that's 1/4 k u1 v1 plus 1/9 k u2 v2, and then I could take the k out. And that's just k times the product of u and v. And that's what we were after. All right, final one. Let's look at it again since it's a bit different from what we've already done. I want to prove that if I take v with itself, I get something bigger than 0. Let's do that first. Then v, that's 1/4 v1 v1, so v1 squared plus 1/9 v2 squared. That's clearly positive. So that's the first thing I need to show. Second, I need to ask myself, when is it exactly 0? Let's do it here. So VV would be 0. That means, well, this here needs to be 0. So V1 squared and V2 squared are 0. So V1 squared is 0 and V2 squared is 0. So that's V1 equals V2 equals 0. And that's the same thing as V being the 0 vector. All right, perfect. So yes, it is an inner product space. I checked all 4 axioms. Good.